Make sure that we record the session. Let me dim the light. I think it's going to be way better. And let's start. Okay. And by the way, Philip, I think you missed this part, which it was for the finite sequences we talked about yesterday. I have posted the recording from yesterday. It's a very easy lesson so far, but I'm just gonna go on to review some very quick points. Then we move on to the new topics. Okay. Now, if you guys remember about the thing that we talked about that yesterday, we said that when we talk about a sequence of numbers, essentially we are looking at an ordered sequence, ordered series of the numbers. For example, as we talked, for example, yesterday, we said that, for example, the numbers, it's going to be, for example, 2, 5, let's say, for example, 2, 5, let's say 8, 11. And we said that, for example, when we look at the next possible number in our sequence, we are essentially searching for a hidden message, which is represented by the pattern of these numbers. We said that, for example, if the ordered series of the numbers which I have starts from 2, 5, 8, 11, then if you look at this, it's very easy to make an inference that what is the hidden message? What is, I should say, the number that it's going to be generated next? What do you think is going to be the hidden message from here, guys? What function represents these pattern of the sequences that we're talking about now? Look at that. Every number, if you see, it is generated by adding number 3 to the previous one. You see, you start from 2, you go to 5 by adding 3 to this. When you are at the 5, you go to 8 by adding 3. And when you are 8, you go to 11 by adding a different number 3. And of course, when you are at 11, you can go to the next box by adding 3, which it makes that if the number there should be how much? Should be 14. And now that's essentially what we talked. But we said that in order to define a finite sequence of the numbers, besides from the fact that we know that they have to just stand in orders, you know by orders that 2 stands here, 5 stands there, you cannot randomly displace these numbers. They have to just stand where they are. You nail them where they are standing. Then the main task which we do is this. The main task has to be, as what we described yesterday, to make an inference. But I mean that to understand what function represents these sequence. From this, you will see that we say that any number, I call that an, is generated as by adding 3 to its previous number. Then I say an minus 1. I hope everyone remembers that we talked about that yesterday. We called these kind of sequences as recursive ones. Recursive ones because you need the prior elements of that sequence in order to get to the next one. That was essentially our full understanding from yesterday, that in order, if you're standing at one element, if you want to go to the next one, you need a function which is a function of the prior elements. For this one, it was very easy because for this one, we said that in order to go to the next item, we need to know the previous elements and add it to the tree. But as also we've proved yesterday and we showed yesterday, for this kind of recursive series, you need a kind of, we brought an example that, for example, you buy a car, you want to drive it, then you need to have some initial gas in your tank in order to drive. We said that your initial gas is going to be this. For example, I give you the first elements of the item, which is going to be 2. Then, based on this representation which I made, then essentially what do we mean is that with this function as a recursive function, and also we call that inaugural or starting element, with the starting elements which is A1, you can make this sequence with infinite number of the elements that you can think of. You start by 2, then subsequently add 3 to each one. We called about these kind of sequences and series as, let's say, we call them as recursive elements. However, in order to continue with this, we are going to introduce a new notation and a new element that is going to be required from what we are going to do today. And this one is this, that we're going to talk about this thing that I'm going to take. But guys, before I move on, do you have any questions from this part of the lesson?
No.
No? Okay. Now, in order to move on, I'm going to, take the same sequence, bring it here. I bring it here, but for this sequence, you see that between these elements, there are a comma. It means that these elements, they are separate from each the other ones. And now, what I'm going to do right now is that I'm going to say, okay, I know the thing which I'm going to do. I'm going to add the elements of my finite series all together. What do I mean? I come here to say 2. It was my first element. You see that? I'm going to add it to the second element, to the 5 plus 8 plus 11 plus 14. I'm going to add them together. What do I get at the end? It doesn't matter, as I'm just going to show that to you what's going to happen. But the thing that you get at the end is going to be, let's say, 7 plus 8 becomes 15. 15 plus 11 becomes 26. 26 plus 14 becomes how much? 50. Correct? That's what I did. It means that sometimes with my series, I'm trying to, with my sequences, I try to add the elements together. In order to add the elements together, I'm going to do what? I'm going to do this one. I'm going to write with a different notation. And please look at this, because you're going to see this notation for the rest of your life anywhere you go. Let me pin my video there. Wherever you go, you're going to see that notation. This notation is this. Look at this. When we talk about this, adding them together, essentially what do I imply by doing this? I mean that what is the word, guys, that I use when I add them together? We use the notation of, we call it sum. Am I right? Sum means adding the terms together, right? If that's going to be that sum, then I'm going to say, okay, I'm just going to use as a notation the first letter of summing these terms together, which is going to be what? Which is going to be S. Which is going to be S. Then I mean that I'm gonna use simple notation as the S, which is the first letter of the sum, in order to let my sequence know, to let my brain know that whenever I see a sequence, a finite sequence, which has finite number of the elements in there, I do not simply look at it. I have to come add term by term. That's what it means, S. But you know, most of the things that we do in the math, we just use a Latin format. We say that instead of writing the S, I'm gonna write a Greek letter which represents the S. And that one is gonna be what? That one is gonna be sigma. Sigma. And I wrote this by this Greek letter. This Greek letter, it is sigma. As you show S in English alphabet, which it represents the sum, in the Greek alphabet, it is equivalent to the sigma, and that's what the Greek people write S as a sigma. Huh? That's what we do. Then this notation, guys, in the math, from now on, it should represent the summation. It means that the elements need to be summed. Then, instead of writing 2 plus 5 plus 8 plus 11 plus 14, which it becomes too tedious to do that. It becomes so much work to add the terms together. Imagine that you have, let's say, 100 elements of that sequence. After 14, you continue with 17, 20, 23, 26, 29, 32, and goes on. It becomes very tedious, and we do not want to write it. Then what I'm gonna do, I'm gonna come to find the hidden message which I got. Look at this hidden message which I got. I'm gonna come to write my hidden message in front of the sigma, which it means that I write the function there, which it means that I'm adding 3 plus a n minus 1. That's right. Then it shows to the sum that this notation is adding all the terms of the sequence, which the sequence is represented by this. However, guys, in your sigma, you have one ceiling as a roof on the head, and you have one thing at the bottom. These two spots represents the number of the elements of in your sequence, which this one starts from, we call that lower limit. This one represents upper limit. What do I mean? For example, in your element, you start, for example, from 2, although I have to change the example because with the recursive series, sometimes the summation doesn't, it's going to be some, I should say, tricky. But it means that, for example, we have how many terms? We start from term 1, 2, 3, 4, 5. We have 5 elements. It means that the difference from the lower limit to the upper limit should be 5. It means that we start from, for example, n equal to element 1. It goes all the way to the element 5, which represents you have 5 elements in your sum. Then you can write at the end all your notation. I'm going to change, I should say, my example. Any questions, guys, so far about the notation of the sigma, which represents adding the terms together?
No.
No questions, everyone? Okay. Now, the thing which I'm going to do now is this. I'm going to go back to the next page. And write this one. I say, guys, look at that. I'm going to introduce you the elements, which is going to be what? Which is going to be represented by this function. We said that an defines a finite sequence which is represented by this function, which is going to be 2n plus 2, where n belongs to what? All the natural numbers, which is 1, which is 2, which is 3, which is 4. This is going to be our basic example to introduce this sequence. The first thing which I'm going to do is that I'm just going to display, that's what I called it, display my finite sequence. By display, what do I mean? Imagine that, for example, you have gone shopping and you have bought some stuff, but the stuff is in your bag, and this one is the bag. You have to put that on the table. And that's what I want to display this, put the items in the bag. How to do that? I'm coming here for the first thing which I do. I'm going to write my elements like that. Okay, I'm just going to put in order to also show that for the Philip, which missed yesterday, I'm going to show this in a way that I make a table. You do not need to necessarily do that, but we are going to do this in a way that it makes apparent of what do we do. It's going to be for the first element. It's going to be for the second element. This one also. This one. I have this one also. I have this one also. And also this one. The first item represents the n. And this one represents an. The first row represents the number which you choose, the number of the elements. And the next one, the next row represents, I should say, the element itself. Okay, I'm going to start because I know that the number of the elements is a natural number because we are counting the numbers. Definitely, it should be an integer. We say element number 1, element number 2. We do not have element number -1 because we do not have -1 students in the class, for example. Then I start with n equals to 1. If n is equal to 1, what is a of n? I put n equal to 1. I get 2 times 1 plus 2 becomes how much? 4. If n is equal to 2, how much is a of 2, a of n?
6.
6. If n is equal to 3, how much is that going to be a of n?
8.
That's right. If n is equal to 4, how much is going to be a of n?
10.
10, that's right, thank you. How about if n is 5?
12.
12. How about n is 6?
14.
14. And how about if is n 7?
16.
16. And we know that as a general, we can write for n, as you saw, it becomes 2n plus 2. That's the general which I write. You do not need to write this in this format as a table because I did this in a way to represent it to the Philip that how the things works when we talk about a finite sequence of numbers. We have a function and we represent it by the number of the elements. Each number of the elements is corresponding to one element in our sequences. Then what do I have? I can show that also in this way. That's another way if you want to prefer to represent it. I can show that in this format, and I say that my a of n is a set of these numbers, which is 4, 6, 8, 10, 12, 14, and 16. That's another way which you can represent it. Either you choose a chart, or you choose, for example, a set notation to represent your finite sequence. But remember, this instruction here, it's a recipe. It gives you all sorts of information that you are interested to find. That's very important criteria. Now, I'm going to extend my work and use the sigma. What do I mean? Please listen very carefully. Then after that, you're going to do some, I should say, some homeworks. Okay. What I'm going to say now is this. I'm going to start from this one, from these elements, from the sets which I created. You sometimes in the math, you are interested to see what is the sum of all the elements which they are extracted from your function. We are in many instances, you will see in future, that you want to see if they are adding together to a complete number. In order to find it, I'm just going to use the summation of this one. I'm going to say, what is that going to be? 4 plus 6 plus 8 plus 10. One way to do that, you're going to say, okay, you write S. There are two options to do that. If you are interested to see what is the summation of these numbers. Guys, please listen to this part. That is very important. In order to show the summation, as a first option, you say, okay, I write it as S. S becomes what? Becomes 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16. This is one way to do that, and there is no argue about this. Sometimes you choose, okay, to show the summation like this. But there is no problem. You can show the summation like that, and nobody's going to say why. It is like as if that, for example, you live at your home, you want to go to the college when the COVID-19 is over. You have two options. Either you can walk, let's say, imagine you are living so far, you can walk for 2 hours, or you can drive to get there by 5 minutes. And the thing which I'm going to do right now is the second one. I'm going to drive, make the things more efficient and more nice and more neat. I'm going to use the summation note as a sigma. I'm going to write sigma. You see, that's the sigma. Everyone sees this notation? Yeah?
Yes.
Awesome. I'm going to write the sigma. What I'm going to write in front of the sigma, it's going to be the function which the sequence is represented. You see that 2n plus 2? I'm going to write this one in front of the sigma, which it shows that that's the hidden message of my finite sequences. Then I'm just going to write this. I'm going to write 2n plus 2 in front of my sigma. But when I write a sigma notation, I need 3 things. First of all, the function of the finite sequence, which represents all about the sequence, then the lower limit, the upper limit. What was the number which I started? Look at this chart which I have. What was the first number which I start for the n? It's n equal to 1, huh? N equal to 1, the starting point, correct? I'm going to write it here. N equals to 1. That's my starting point. Where did I end up, guys? By n equal to 7, huh? Then I write it on the top of the sigma, that it shows that I started from n equal to 1, and I end at n equal to 7. That's why we call this the lower, the upper. You start from n equal to 1, go all the way to the n equal to 7. Then it's going to be very easy then. Then what do I write? It's essentially the same thing. Let me, give me a second. I just put that into the calculator to see what do I get for the sum. Guys, anybody has a calculator handy? Rose,
Yes.
can you please put this one in calculator? 4 plus 6 plus 8.
Yes.
I think it's going to be 70. You do that also?
Yes, 70.
70? Okay. Then I can say that it's going to be what? It's going to be 70, the summation. It's going to be 70. And also, we know that it's going to be also 70. Then you see that, guys, when you have a finite sequence of elements, you can use two different notation when you want to add the elements. The first one is that you are doing this one. You say that I'm going to put S, and you show that explicitly all elements which is sum, or you can squeeze it into this notation. These two are the same, except the fact that with the sigma, when you write the function and the lower and upper limit, the sigma shows to your brain that, okay, you are going to start by n equal to 1, and at n equal to 7, find all the elements of this series and add them together. And the output of that function, it becomes 70. Does it make sense to everyone?
Yes.
Thanks, Rose. How about Gloria, Philip, and Ferris?
Yes.
Awesome. I am so glad to hear it. Okay, if you have no questions, we just do one problem. Then we do some exercises and we go for the break. Okay, now. Let's do one exercise. Guys, I want to ask you, as an exercise, I'm going to give you this series. That, for example, the first one, it just becomes 1 plus 3 plus 5 plus 7 plus 9. Okay, guys, can you please take some time and try to write this one in terms of the summation that we talked about? Okay, I'm gonna also start it myself. Okay, I'm gonna do that for you because after the break, you have lots of opportunity to do the practices. Look at this one, guys. For these elements, 1 plus 3 plus 5 plus 7 plus 9, if it was a finite sequence, what is the function which represents my sequence? I mean, as a of n, we have odd numbers. Can I write it as odd numbers be written as 2n minus 1, where we have n belonging to all the natural number? Can I say that? Yes? Is it clear for everyone? I have, let's say, I have here a of n, I have n, I have a of n. Guys, look at that. If I have n equal to 1, 2, 3, 4, and 5. Guys, look at this one. If I put n equal to, let's say, if I put n equal to 1 in this function, what is going to be a of n? Huh?
1.
1, correct. If I put n equal to 2,
3.
3, n equal to 5. Sorry, by 2 becomes 3, by 3 becomes how much?
5.
5, by 4.
7.
7, by 5.
9.
9. You see that this function can create these elements. However, I'm just going to add them together because the task which is required for me is this, that I want to find another way to write them. I want to show what happens if I want to add them together. 1 plus 3 plus 5 plus 7 plus 9. Right? Then that's the task. In order to do the task, we notice that for summation, I can use sigma. In front of the sigma, what do I have to write? The function 2n minus 1. What is going to be my lower limit? What is the lower limit, guys? Philip, Gloria, Ferris, and Rose. The lower limit is n equal to 1. Where my n ends in this chart? Is it n equal to 5? Then n equals to 5, then this is going to be this. Then you see that. When you see this notation, your brain says that expand this sum by adding n from 1 to 5, then add them together like this. Does it make sense, everyone?
Yes.
Yes? How about Gloria, Ferris, and Philip?
Yes.
Yes? How about Chen Chen?
Yes.
Philip and Ferris, how about you two, man? Okay. I have a text here. Let me see. Who is that? Okay, thanks. Okay, guys. Now, I think, what time is it now? I think that's a good timing to stop. Go for the break. Please, guys, come back by 12:20. Sounds good?
Yes.
Awesome. Then I see you guys in 15 minutes then.